So I'm going to show you how to do problem 20 from chapter 8. I recopied the problem here. It says, a hungry 700 Newton bear walks out on a beam in an attempt to retrieve some goodies hanging at the end. The beam is uniform, weighs 200 newtons, and is 6 meters long. The goodies weigh 80 newtons. A, draw a free body diagram of the beam. B, when the bear is at x equals 1 meters, find the tension of the wire and the components of the reaction force at the hinge. And C, if the wire can withstand a maximum tension of 900 newtons, what is the maximum distance the bear can walk before the wire breaks? So I copied a diagram here. Here's our little bear, 700 newtons, the beam is 200 newtons, the goodies are 880 newtons. Here's the wire at 60 degrees. The bear is 1 meter and the entire beam is 6 meters. So here I kind of started the free body diagram. We just need to add the forces. So I'm going to start with the mass of the bear. That's his weight going down, and they give it to us in newtons, so it's already 7 newtons, but 700 newtons we know, but I'm just going to call it M1. And then we have the mass of the bar, or the beam, which we'll label as M2. And then we have the mass of the goodies, which I'll label as M3. And then we have the tension of the rope, or the string, I think it's rope. And then we have the components of this, which this will be tension cosine, or it's not theta, sorry, it's 60, because we know it's 60 degrees. And this will be tension sine 60. And then we have to do the reaction from the tension. So we have a force here, which is the reaction force, and we have to find the components in the next portion. So let's draw those into r cosine theta and r sine theta. Okay, so there's our free body diagram. Oh, and you have to mark our positive y and positive x. Okay, so now let's do B, part B. When the bear is at x equals 1 meters, find the tension of the wire and the components of the reaction force at the hinge. So we're finding these two components and tension. So I'm going to start by, since we just made our free body diagram, finding the forces in the x direction. So the sum of all forces of x equals, the only two forces that we have in the x direction are r cosine theta and t cosine 60. So r cosine theta minus t cosine tension cosine 60. And this will be 0 because our equation's in equilibrium. And then we can bring this over, make them equal each other. So our reaction component for the cosine will equal tension cosine 60, but we need to find tension. So now I'm going to make another equation in the y direction. Sum of all forces y equal. So we have a lot of forces in the y direction. I'm going to start with the r sine theta, which is positive going up, and the tension cosine 60 also going up, subtracted by mass 1, mass 2, and mass 3. And so the sum of all forces will equal 0 because it's in equilibrium, and we don't know r sine theta, and we actually, or I guess I could write these out, t cosine 60, and we know the masses of 200 newtons and 700 newtons and 80 newtons. But we don't know these two things, so I'm going to try the torque equation to see if we can find one of these variables. So with the torque equation, the sum of all torques, we have our three masses again. So those are going down, so they're negative RMI minus RM2 minus RM3, and then plus we have our reaction force and our tension force. So I'm going to take the torque from over here, which will be 0 for the reaction force. So the sum of all torques equals 0 because it's in equilibrium. -1 meter times 700 newtons minus 3 meters times 200 newtons plus this one's, the reaction will just get canceled because that's where we're taking the torque. Plus 6 meters times tension. So now this lets us isolate tension and find tension because that's the only variable left because this is canceled out. So we can simplify to this. If you plug it into your calculator, and then we can further simplify to find tension, which is approximately 342.56 newtons. So now that we have tension, we can plug tension back into this formula to find the cosine component of the reaction force. And if you plug that into your calculator, you should get 171.28 newtons. And then if we go back to our sum of all forces in the y direction, we have r sine theta plus 342.56 newtons cosine 60, and if you add these all together, you get 900. I guess subtract them all together, you get 980. And then if you isolate r sine theta and plug it into your calculator, you should get 683.33 newtons. And so now for part C, if the wire can withstand a maximum tension of 900 newtons, what is the maximum distance the bear can walk before the wire breaks? So because we're talking about distance here, I'm going to use the torque equation because there's the torque equation includes R, which is distance. So tension equals, I'm going to start with the masses, just copy down this same equation, but X is the distance from mass 1, the bear, which is what we're trying to find. So xm1 minus rm2 minus rm3 plus r of the reaction force plus r tangent sine 60. And these all should have sine 90s, but since that just equals 1, I just decided to keep them out. But technically the equation for torque is r sine theta. So then the sum of all torques will equal 0. And the mass of the bear is 700 newtons. X is the distance we're trying to find, minus 200 newtons of the beam, 3 meters. You take the distance of the beam in the very middle, which is 3 meters on either side because the beam's 6 meters. The reaction force gets canceled out again. And because they told us that the tension force is 900 newtons, we use that. So a distance of 6 meters times 900 newtons times sine 60. And actually, if you take 700, this part is what we're trying to find, so I'm going to bring it to the other side. And then if you do some simplifying on this side, you should get 3,596.54 newton meters. And then if you divide 700 newtons, your X equals 5.14 meters. So the bear can walk 5.14 meters before the beam breaks. So it looks like he'll never get his goodies. Okay, thank you. Hope this helped.